We study X15Q, statics and elasticity. A cylinder of mass m, this is a cylinder cross-sectional view of a cylinder, and radius a is in equilibrium as shown in the cross-sectional figure without friction. The normal force at contact points, there are two contact points, A and B. There is normal force applied here at A and here at B. Normal means it is always perpendicular to this plane. Although it is a straight line, it is just a cross-section of a vertical cross-section of a plane, respectively. Discuss the conditions of the equilibrium. Okay, so here there is a normal force applied, and left and right we have angle, the slope and the horizontal plane makes an angle, the same angle, so there is a left-right symmetry. So there should be some normal force applied in here, and another normal force that must be symmetry will be on the left hand side, and this normal force attach the subscript b. It should be the same in magnitude and making an angle, the right angle with respect to the slope. In addition, we are under a constant gravitational field, so this rigid body experiences the gravitational force mg because the mass is m. And when we study a rigid body dynamics or statics, in here we are considering statics instead of dynamics, it doesn't move at all. The gravitational force is applied at the center, that means center of mass. So this rigid body accepts the three kinds of force. So we have NA, a vector, and NB, and mg. These three forces applies as an external force. And because the system is in equilibrium, we have two constraints. The net force applied to this rigid body must be 0. And the net torque applied to this rigid body is 0. So this is the equilibrium condition. Okay, so we are all set. Let us return to the equilibrium condition for the net force. The sum of the three forces is 0. If I translate these two forces, then I can always construct a triangle. NA and down, MG here, and NB. So we know the magnitude of these two forces are the same. So any three forces constructing the equilibrium, if I translate the three sides of forces appropriately, then I can construct a triangle. In addition, because of the symmetry of this system, magnitude of A and magnitude of B, they are the same. So this triangle, isosceles triangle. Okay, so angle, and this angle must be the same. So we are almost there. First of all, the net force vanishes, therefore the algebraic sum of the three forces should be 0. Next, because they construct a triangle, area of the triangle can be computed by making use of cross product. So in here, this is the area of the triangle. The area of triangle can be computed with x to 1/2 times the absolute value of a cross b when a, b, c construct a triangle. When they construct a triangle, then the sum of them should be 0. Sure, if it is possible to construct a triangle in such a manner, C and minus B and A. In this case too, because I take the magnitude, so it is the same as whether I choose A cross B or A cross minus B, because I take the magnitude of the cross product of two side vectors. Okay. So using this relations, substituting NA, NB, and MG for these A, B, and C, we find that cross product of AB, BG, GA. These three cross products must be the same. So they are the same even in the case we have this sign is also okay. A cross B, A, B, and the orientation is positive, and B and C, and translate this one to find B is there. B cross C, orientation is still counterclockwise, and C and A, orientation is still counterclockwise. I mean, when I take the orientation, it should span from a vector to another vector along the angle. There's a smaller. This is a greater, and this is a smaller angle to make a full angle. Okay. We have another constraint. We have NA in here and the angle between NA and G. So this is the angle. This is the angle between NA and G. And then NB and G. NB is in here. And we translate this one here because of the symmetry. So NB, this is NB, and gravitational force. So this angle, these two angles are the same. That's fine. And then, let me erase everything. It's too busy. Theta is in here. This is a right triangle. Where is NA? NA. This is direction of G, and let us choose NB direction. NB is here. This one has a right angle, and this is the theta. And this is right angle. So let me call this as X. Theta plus X equals 90 degrees. And this is a triangle, a right triangle. The sum of these two angles must be another right angle. So this should be y, and that y. Right angle. Subtract. We find that theta equals y. So this angle is the same as this angle. Okay, we are ready to solve this problem. Because this angle is a theta and there is a symmetry, this angle is also theta. And again, theta, theta. So as a result, the angle between NA and NB, this angle is 2 theta. Okay? All set. We are ready to solve the problem now. Okay, we took a very long time to pass page 1. So let us compute the area of a triangle. The area of triangle is 1/2 magnitude of one side and magnitude of the other side, and multiplied by sine theta, where theta is the angle between the two vectors. Because we have A and B, an angle theta, then the base times the height multiplied by 1/2. So because 1/2 appears everywhere, it's better to consider AB sine theta AB, BC sine theta BC, CA sine theta CA, something like that. So we use this relation, NA times mg sine pi minus theta. So there is a sine theta. Sine theta. Again, we can make use of this one. We have identical relation, NBMG sine theta. And then the angle between NA and B is 2 theta. So we have a product of the magnitudes of the two vectors multiplied by sine 2 theta. All right. So because of that, in addition, we have a symmetry that magnitude of the two normal forces are the same. Therefore, I can divide these identities with NA, either NA or NB, they are the same. So if I divide them, then divide this expression with NA and B, what I obtain is mg sine theta over NA equals sine 2 theta. You know, sine alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha. And if I substitute alpha beta equals theta, I have sine 2 theta, and this one is 2 times the sine theta cosine theta. As a result, I have this relation. All right. If I consider this identity, sine theta cancels. And what I obtain is this. 2 cosine theta becomes in the denominator, and this one is pulled out to the right hand side. So magnitude of NA and NB are both mg over 2 cosine theta. For example, if theta equals 0, it becomes flat. Then this one touches the ground, and we do not distinguish A and B. That is only a single point. So in that case, this NA is mg over 2, and NB is mg over 2. Two constraint forces must be added to construct the sum multiplied by 2 is mg. Okay, that's reasonable. So this normal forces is heading this direction, but when angle reaches 0, the two forces becomes parallel and the same, and half of each of them is 1/2 of mg, and if I add them up, we can sustain the gravitational force mg. Okay, next we have the angle between NA and G. That is already obtained like that. The angle between NA and B is 2 pi. As a result, I can construct the explicit notation for if I have the magnitude in here, I can find out the unit normal vector along the direction of NA and NB. Let's see. This is, we have angle theta, and this one is the theta. This is NA, direction of NA. Okay. This is direction of NB. This is theta. If I draw a horizontal line, what is this? This is 1/2 of pi minus theta. So this direction is it should be NB in this case. This should be NA. Okay, in here, what's that? This is the theta. So this angle is 1/2 of pi plus theta. Okay, because of that, direction of NA, this direction of NB, and this is the direction of NA. Direction of NA is a backward, so negative sign on the x-axis, and it is along the z-axis is a positive, and because the angle is 1/2 of pi plus theta, therefore I must exchange cosine and sine. In the case of NB, y component is the same and x component is to the right, so there is a sign change. If I absorb this denominator cosine theta inside the parentheses, then I would get tangent both sides, both cases, and cosine cancels in the vertical direction. Okay, we conclude that I have constructed the explicit value for NA, NB, and I know what mg is. Mg is along the minus E2 direction. This vector. So using this one, we can check whether our previous calculation for NA, NB, and mg satisfies the original constraint of the cross product of two sides are all the same. And you can carry out explicit calculation for this. The final result is like that. The reason why we have a negative sign is the direction of NA is here and NB is here. So if I make a cross product NA cross NB, this direction is a clockwise direction. So spanning the vector to overlap to find out the direction of the normal vector says that it is counterclockwise and the direction is negative. It is along the negative E3 direction that is going into the paper screen. Alright, we can copy the magnitude of NA, written in here, copy this, and sine 2 theta can be expressed as 2 times the sine theta cosine theta. So we can simplify this relation. There are 2 cosines in the denominator. So my final result is a cosine theta, single cosine theta, and 4 in the denominator, 2, so 1/2. And then mg total square, and we have sine theta in the numerator, that is tangent theta. So we can make use of that fact to compute some more. So let me leave it up to you. Torque. Next one is to compute the torque. Oh, it's better to consider this problem for considering torque, and you can apply the same or similar, very similar method to solve this problem with the different angles. I don't have to repeat the problem 2. Instead, let us finish the part of the problem 1, including the torque. Now we have found the direction. We have identified the direction of NB and an A, something like that. So we have an origin at the center of the cylinder. So first, AO. We have AO. This is AO. So this is the direction of NA. Now, this is what we have already computed. And we would like to find out, let us read it through because the system is in equilibrium. Okay, the net torque must vanish too. That's fine. We must choose an axis of rotation to compute the torque. For example, in here, we can choose the axis perpendicular to the plane and passing the point A. Okay, so we do not choose the reference point to compute the torque as the center of mass. Instead, we have chosen this point. When solving a problem regarding the torque depends on the reference point through which the axis of rotation passes. So we should be careful. We do not want to change the axis of rotation part by part. So when we consider every force, we must keep the same axis of rotation. So if I choose the axis of rotation passing through the A, then there is a force NA that does not have to be. We do not consider this because the lever arm vector of this force relative to the axis of rotation. This is passing through the axis of rotation. So this contribution vanishes. The remaining 2 pieces are gravitational force, and lever arm vector is this part, and another force is NB. This is NB, and lever arm vector, because it is in here, lever arm vector, we need to find the right angle to find the perpendicular distance, that is lever arm, magnitude of the lever arm vector. So NB multiplied by this and this one. If you look at this reference point A, NB tends to rotate this one clockwise, and gravitational force tends to rotate this cylinder anti-clockwise, and these 2 torque must cancel. That is our constraint to solve the problem. So we know what this is, and the first torque mg, and this is A, and this is making a right angle, AO. this vector, and the action of this gravitational force applies to at the center of mass. So this mg is written here. This is x cross f. That is the torque due to mg. mg gives the torque like that. Okay. Alright, so I substitute this one, and the gravitational force is minus mg minus 2. So minus e hat direction is downward. So I compute mga and e1 cross e2 minus plus, and e1 cross e2 is e3. We keep the sign. However, e2 cross e2 vanishes. It doesn't contribute at all. So this is the torque due to the gravitational force applied to the center of mass relative to the axis of rotation passing through A, and that is perpendicular to this plane. Okay, we know where A is and where B is. If I subtract B from A, then I can find the direction of this, A and B. So reference point is A, and we have point B, and no more force at B is applied like that. So when I compute the torque due to this NB relative to this axis rotation passing through A, we need to multiply x cross F, that is the torque applied by NB, and this force is AB is here. I copied this value, and NB, we know what NB is. NB is given in here. I copied that result in here, and E1 cross E1 cancels, and E1 cross E2 becomes E3. However, we have a negative sign on it. 2, 1/2, they cancel, and we find this. Finally, if I add these two partial torques, the magnitude is the same, but direction is opposite, negative, positive. They cancel exactly. Therefore, we have proved that the force, normal force, we have obtained the normal force, and we have found that the two normal forces and the gravitational force acting on the center of mass exactly cancels as a force and exactly cancels as a torque as well. That's it for today.